Hi, everyone. We're going to get started. Thank you again for joining us at the 2022 Sloan Sports Analytics Conference. The Competitive Advantage talks are presented by Kager, also known as Craft Analytics Group. My name is Jen Whaley, and I'm a first-year MBA student at MIT Sloan. It's my pleasure to introduce the presentation, 3D Motion Analysis Finally Has a Magic Camera, a pioneer's journey of how we finally got here. Please join me in welcoming our speaker, Phil Cheatham, Chief Scientist for SPORTSBOX AI, to the stage.
Thank you, Jen. Well, welcome, and I'm going to spend about the next half hour talking about motion analysis and kind of how we got from the early days to where we are today with the so-called magic camera. I've been active in the field for 40 years now, since about 1980, so I've watched the technology develop from the early days and from the tedious, time-consuming systems where we had to put markers or sensors or wires all over the athlete, and that would inhibit their motion and slow their training sessions down, to finally today where we can now do it without being intrusive whatsoever with having what I call the magic camera. While I was going through my journey, I was always thinking about, wouldn't it be cool if we could have a camera that you could just point and shoot the video and immediately get all the data? Well, it's actually, I thought it was impossible. I didn't think it was going to happen, but it has happened, and I'll talk about it today, and I'll talk about how we actually got there. So let's get going. First though, excuse me, a little bit of my background. I am an Olympian in gymnastics for Australia. I competed in 1976 in the Montreal Olympic Games. And yes, that's me, my gymnastics me there holding an iron cross in Montreal back in the day. Can't do that anymore. I have an electrical engineering degree, and hence my interest in technology. I also then went on to get my master's and PhD in biomechanics because I was able to put sports and engineering together, and that was the perfect mix. You can see, though, from my background that I've had various different jobs along the way. I've been the research engineer at the US Olympic Committee back in the 80s, became an entrepreneur and started several of my own companies in motion analysis, and then finally went back to the US Olympic Committee again for the last 10 years, since about 2010, being sport technologist out at Chula Vista Olympic Training Center, and then ending up the last few years as the director of sport technology and innovation. But finally, as I said, talking about the magic camera, I met the people from SPORTSBOX, and they were in the very, very early stages of developing the technology, and they invited me to come along and be the chief science officer because of my biomechanics background. So that was an opportunity that I jumped at, and that's where I am today. But let's go back again, like I said, to the early stages and have a look how we got there and what the journey was. As I said, I started out back in the 1980s. I was a gymnast, and I was lucky enough to train at Arizona State University in Tempe, Arizona. That was one of the top gymnastics teams, collegiate teams in the country at the time. Had some world champions training there. Kurt Thomas was training there. And so for me to be able to train there in preparation for the next Olympic Games, which was the 1980 Olympic Games, was wonderful. And so when I came back after, I didn't compete in the Olympics in 1980 because that was the year of the boycott, unfortunately. But I was able to come back to Arizona State University and work as the assistant coach, and at the same time do my master's degree in biomechanics. So when I got there, I found that they had a whole bunch of equipment. As you can see, they had a high-speed camera, film camera, a digitizing tablet, a computer that had a massive 64K of memory, and they had a projector. And so they had all the pieces and parts to make a motion analysis system, but no software and no interfacing. So in order to get my master's degree, I learned very quickly how to write code and develop a motion capture system. It was a very tedious process. You'd have to put the cursor on each joint one by one by one, and then advance to the next frame and keep going one frame at a time. So it literally take you hours to analyze a single skill. But I did complete the software and was able to create a software package that was able to do nice animations, like you could see there, stick figure animations, which was pretty exciting for me back then because I thought it was pretty cool. But it also allowed me to calculate velocities and angles and distances and heights and spin rates and those sorts of things. So that allowed me to do my master's thesis, which was effectively looking at what the input was to what the output was. What was the pre-flight parameters, the velocities coming in, and how did they affect the velocity and the height and the distance and the spin rate on the post-flight. And that was very helpful because I found several things that were important that had, some of them were obvious. One of them being that the faster you run, the more distance you're going to fly at the end of the horse after you've taken off from the horse itself. But one of the other questions that I answered, which wasn't quite so obvious, in fact, it was counter to what was typically thought at that point in time, and that was that you had to push off the horse really hard with your arms so that you get more height to do your flip and land on the other side and get more rotation. It turns out that that's not the case, and I proved that by plotting the center of gravity of the gymnast through the vault, and found that the center of gravity never came down at all. It hardly even had a point of inflection when you were hitting the horse. So basically, you didn't prop off the horse. You didn't block off the horse. You actually kind of just tapped the horse on the way through. So what you were really doing was a double front somersault with just kind of a tap on the way through. Now, if I'd have known that back then, it would have made a lot of difference in how much height and spin rate you could get in the post-flight. But that was exciting because I was actually able to contribute to the field somewhat. One of my professors was an advisor to the US Olympic Committee in sports science. He was a sports psychologist. He took us on a field trip to the Olympic Training Center in Colorado Springs way back in the early 80s, like I think that was 1982. And I was very excited by all the things we could do there, and I was later offered a job to be the research engineer, and I snapped that position up. And we had state-of-the-art technology back then, which was an IBM PC-XT and a VCR, a video, if you know what a VCR is anymore, a video cassette recorder. And I was able to take, by the way, that's my young engineering me, sitting next to the IBM PC with the digitizing tablet to my left hand and a picture of the VCR in the back there. I was able to interface those two together with a video controller card, which I plugged into the PC, and an image capture card, which I also plugged in. And so I was able to control which frames I would capture, put them on the screen, superimpose the cursor on the screen, and plot out my stick figure frame by frame by frame. Still tedious, but it had never been done before with video because we were doing it with film, and film was very, very costly and time-consuming to get done. So this allowed us now to analyze our athletes when they would come in for camps, and we had to get to the data to them by the next day. So we would stay up all night digitizing, but at least we didn't have to send the film out to get developed, and we could take as much video as we wanted to. So that was definitely a step forward. In fact, it was so much of a step forward that myself and the biomechanist, my co-worker, decided to form our own company and start marketing this particular concept and this particular software package. Although we did rewrite the software from the ground up and started again with 2D manual digitizing. But then we very quickly advanced to 3D digitizing. Now, how do you get 3D for motion analysis purposes? Well, you have to have at least 2 cameras, and they have to have different points of view, and you have to film a calibration frame to start with. That's that funny Sputnik-looking thing in the dark picture on the right side there. So those are known coordinates. You would film from each camera, and you would do the 2D manual digitizing process that I talked about from each camera, from each different view of that calibration frame. And then there's an algorithm called the DLT, the direct linear transform, that would put those together and form a three-dimensional space, X, Y, and Z. And then you could take that calibration frame out and film any motion now. And now you could turn it into 3D. So you could get, you know, a running, a jumping, a throwing, whatever motion you wanted to analyze, and get it in 3D now, not just 2 dimensions. So that was a big step forward. And I'll talk about an application of that in just a minute. But not only that, we went to the next step, and we wanted to do automatic tracking. So we used the same 3D technology, but this time we used reflective markers that would fluoresce brightly when a spotlight was shined on them. So now, instead of having to mark the points manually, the computer could find them, because each image is really just an XY array, just like a spreadsheet basically, and each cell has a pixel, and each pixel has a brightness, and each brightness level is represented by a number. So 255 might be white, and 0 might be black, and there's a whole grayscale in between. So all the computer has to do is search through that spreadsheet or those XY cells and come out with the ones that are brighter than a specific threshold. And then once it's conglomerated them in specific locations, it can find the centroid of each one and give an XY coordinate of each one automatically so that the user doesn't have to do it. And that was another great breakthrough. We weren't the only ones doing it at the time. There were a couple of other companies called Motion Analysis Corporation, Vicon, Qualisys, and also later on a company called Gears is doing it for golf. But we were one of the first. And we even got offered the ability to do research at the Barcelona Olympic Games in 1992. Now, as you can probably imagine, we couldn't go putting reflective markers on the gymnasts while they were competing in the hall. So we had to revert back to our manual mode, which was the point by point by point tracking. But the cool thing was, we could do it without the gymnasts even knowing they were being analyzed. So we put 6 cameras up in the stands. We filmed our calibration frame in the morning before the gymnasts arrived, took it away, and then when the gymnasts were competing, we were capturing their film. We weren't doing any digitizing on the spot. We took it back to the lab, and we stayed up all night digitizing 1 or 2 skills, because now instead of just 1 camera, you had 6 cameras you had to do, so it took a long time. But we were able to put high bar dismounts and release regrasp skills, where they do the flip and then they catch the bar again. We were able to put those on TV the next morning, superimposed on an avatar. So this was back in 1992. So I think we were maybe one of the first groups that got it on TV. But it was very exciting. Not only did we get on TV, but we actually got research papers that we published from that work, looking at the timing of the release skills and the velocity of the release skills, because these were brand new back then. There was only a few gymnasts doing them, and they were very difficult. So after a while, though, and continuing the story, I started to get disillusioned with the optical systems, because they were still very limited. You had to put the markers on, and if the camera could not see a marker, then you couldn't track it. So basically, we had to connect trajectories together. Sometimes the trajectories would flip. And so I was looking for a new technology that would be much more efficient. And we found this electromagnetic technology, where now you have a sensor and a transmitter. And the sensor is 3 coils of wire transmitting an electromagnetic field. And the little sensor can pick up that magnetic field and give you the X, Y, Z, and also pitch your own roll. So it can create a reference frame which allows us to give much more information than just a single point. So that was a breakthrough for us, and we worked with a group called Titleist Performance Institute, and we had a system at their facility, and we would now capture golfers. So golfing was pretty exciting, because we thought, hey, this is going to sell lots and lots of systems. And so we worked with the Titleist Performance Institute, and we developed an algorithm called the Kinematic Sequence, which allowed us to look at the efficiency of the golf swing. And so if you look at the curve on the bottom right of the screen, you can see 4 curves, a red, green, and blue curve, and then a brown curve. And what the red curve is the rotational speed of the pelvis or the hips. The green curve is the rotational speed of the rib cage, the chest, and the blue curve is the swinging speed of the lead arm, and the brown curve is the swinging speed of the shaft of the club. These are all in degrees per second, so these are rotational speeds, not miles per hour. And so you can see that it actually is a very clean curve. And from the kinematic sequence, I can immediately look at a curve and tell you whether that's a novice golfer or a pro golfer, because you can see how nicely they accelerate and decelerate. By accelerate, the gray area in the middle is the downswing. So by accelerate, I mean the curve goes up, and decelerate, the curve goes down, because it's velocity. And if the velocity gets faster, you're accelerating, and so on. And you can see how there's a nice sequence from the red dot to the green dot to the blue dot, and finally to the peak at impact. And so what's happening is the body is transferring energy from the ground up. The pelvis rotates first. It gets the speed going. It's like the first gear, if you like, in a manual stick-shift transmission. And then the core muscles, the abs, they transmit the energy, and the strength of the abs transmits it to the chest. And so now the chest gets a bump in speed. And then the same happens with the chest. And by the way, when that part of the body is accelerating and transfers the energy to the next part of the body, that actually decelerates the previous part of the body, because the previous body is accelerating and it has to push on something. So it slows the previous one down. Hence the hill, a bigger hill, until you finally get to a mountain. And so that kinematic sequence was used by the Titleist Performance Institute and kind of became a standard of efficiency in the golf swing. And we were able to measure that and do several research papers. One research paper we did was to prove that it was a difference in the kinematic sequence between, between novices and elite golfers. And you can see there a bunch of numbers that have been extracted from those 4 curves in the kinematic sequence. We've got the accelerations, we've got the decelerations of each body part, we've got the maximum rotational speeds, and we've got the rotational speed gain, how much speed was gained from one segment to the next across each joint. And we in fact did, in every case except one, we found that there was a significant difference between the novices and the pros in the accelerations, in the decelerations, the speed gains, and so on. So this kind of proved the efficacy of the fact that the kinematic sequence was in fact a performance indicator, able to show us the difference in performance between novices and elites. We didn't find a significant difference in the timing. We thought there'd be a difference between the timing of the peaks, because after all, it is called the kinematic sequence. And so we thought the sequencing, the pelvis peaks first, then the chest peaks next, and then the arm peaks. And we found that as a trend. And we certainly did find it as a trend in the pros. And in the novices, we found that the arms would peak before the chest. So typically a novice likes to throw the club, cast the club, and so we were able to see that difference in the timing. It wasn't a significant difference, but it was definitely a difference that we could see. So moving on in time now, we're in the 2015 to 2021 time era now. Unfortunately, because the AMM system, the wires and the sensors and the TPI, the Titleist Performance Institute system that we developed, was time-consuming to set up. It would take about 15 minutes to set up a golfer. We'd have to put all the wires on. We have to digitize the different parts on the body so that we'd scale the model. And that took a while. And then there was also the optical-based systems, and they had problems, as I mentioned. If you can't see a marker, you can't track it. So in the case of the optical systems, there was still a lot of post-processing to do. So to be honest with you, I got a little bit annoyed, I guess, with those forms of motion capture. And when I went to work back at the Olympic Committee again in 2010, I started focusing on different technologies. And one of the technologies we focused on was the radar projectile motion, the TrackMan and the flight scope systems that were being used in golf to track the flight of the ball. I was working at the Olympic Training Center as the technologist, as I mentioned, and one of the groups that we were working with was the Olympic shot putters. And it just so happened that we had 3 of the top shot putters in the world at the training center. And so we were able to get a grant from our Technology and Innovation Fund and produce or have TrackMan and FlightScope produce a version of their technology that we could use for the throw sports, specifically in this case, shot put. And so it was able to give us the release velocity, the angle of release, the direction of release, how high it was the release. And those are very important parameters. Of course, if you know anything about physics, the projectile motion of a shot put is determined entirely by those 5, or the distance that the shot put goes is defined by those 4 input variables. So we worked on a regular basis with the shot putters. In fact, it became inherent in their training. It became part of their training. And one of the guys that we worked with, Ryan Krauser, actually became, he was a world champion, but he actually broke the Olympic record just before Tokyo last year at the Olympic trials. He'd been knocking on the door for a very, very long time. In fact, in Tucson, at the Tucson Elite Classic, a couple of months before the Olympic trials, he threw 23 meters, which was the first time that had been done this century. Nobody had broken the record because it was set back in 1992, back then when they were not testing for doping very much at all. And so we didn't think that record was going to be broken for a very, very long time. But he did. And the cool thing was, I was there to see it, and I was able to get the data from it. So you are actually seeing this. This is the first time we've released this data. I asked Ryan if I could talk about it, and he said, yeah, sure, go ahead. I'm going to do better now anyway. So that's old news. That's old data. But at the Tucson Elite Classic, I started that story. He was throwing at about 33 degrees, which was too low. It needed to be 34, 35, 36 degrees to get the most distance. And he was throwing at about 14.5 meters per second. So literally, from our evaluation at the Tucson Classic, I told Ryan and his coach Mitch that if he just increased his angle by about 1 degree, he was throwing at 33 degrees, and if he increased his speed by about 1/10 of a meter per second or 2/10 of a meter per second, he would break the world record. And that's exactly what he did. So it was pretty cool to see the fact that we predicted what was going to happen, and we told him the numbers he needed, and those were exactly the numbers that actually came out when we captured the world record. Now, another project that I'm going to go on to is the first application of video and AI. We teamed up with Southwest Research Institute engineers. We got 3 of them in the front here that worked with me on this particular project. And we started analyzing diving. Now, I talked about the magic camera. I'm finally getting to talk about the magic camera. Here, we were able to put a single camera, anywhere in the stands, film the video of the diver, and then automatically capture the stick figure that we talked about. This was pretty exciting because this is, again, one of the first times this has been done, especially for diving. And then before we would do the analysis, it would take us hours to do the digitizing. Now we can present the data pretty quickly after the dives. The idea was to have a training session. They'd dive in the morning, we'd get the data, and we'd give them the data in the afternoon. One of the divers, Andrew Capobianco, actually won a silver medal in Tokyo, and we were able to give him some feedback on one of his dives, actually a couple of his dives, but this is the best example. A forward 4.5 somersault. They need these very high degree of difficulty dives in order to score high and win a medal. And we were able to tell him the difference between his bogey dive and his eagle dive. His coach was a golfer, and so he liked to classify the dives as bogey and eagle dives. And the bogey dive was leaning too far forward, and so we could measure the distance from the end of the board to the center of gravity, and we could literally tell him Okay, this one's 12 inches away, this one's 6 inches away, and the 6 inches was much better because it allowed him to get more height and distance. And so we could feed that information back instead of just saying, oh, I think you were leaning too far forward. Much more quantitative. Okay, so finally we get on now to the magic camera that can capture three-dimensional motion analysis with just a single camera. This is the company I'm currently working for, called SPORTSBOX, and the product is 3D Golf. So it's a markerless-based motion analysis system where, as I said, you can literally, as you can see on the screen, you can film a single, the front view of a golf swing, and it turns it into 3D, a 3D avatar with the calculations of the kinematic parameters, such as how much turn you've got, how much swing velocity. We're going to be working on the kinematic sequence, but we can tell you how much sway, thrust, and lift, and all of these directly from, with no intervention to the athlete. So this is, in my mind, something that I've been hoping for many, many years, and it's finally arrived. We basically have two AI models, one that does the 2D pose estimation, and then we have a second AI model that takes the 2D pose estimation and turns it into 3D. One quick example, about one more minute and I'll be finished, is that we can calculate these kinematic trackers. And one of the things we look at is we've created a database that allows us to correlate to swing speed and distance. And so we can come out with what we call the absolute tracker truths. And we have this table that we can compare your golfer to what the best tour pros do in the world. And so, for example, here's one called chest sway. And we can see that chest sway travels towards the target during the downswing, but then rapidly moves away from the target as the club releases. And we can give the golfer those values. And so we can immediately see if there's going to be any differential or any difference between what your golfer is doing and what's expected of the norms. We don't say teach to the mean or teach to the average, but these average values do give us a range to look at. And now the instructor can literally take this to the driving, not only the driving range, but they can take it out on the field, on the course with them. And so that's where we've ended up. And that's the journey. It's taken 40 years to get there, but we're finally there. And I think it's going to be very exciting in the future. And I believe that the magic camera has finally been invented. Thank you.
We have time for a few questions if anyone would like to ask Phil anything.
Hi, Phil. Great talk. That was really exciting. My name's Sarah, and I just had a question about the data itself, especially using a camera, as you know, to get angles that are out of plane. It makes me a little bit nervous because I'm a Qualisys user through and through. And so I was wondering if you could speak to the repeatability and the validity of that out-of-plane data using a 2D camera.
Yes. As you saw, I was a developer of the AMM, the three-dimensional system that used the electromagnetic sensors. So we are using the electromagnetic system as our ground truth to compare the data we're getting from the 3D cameras. And obviously, with one camera, it can't be as accurate as multiple cameras or an electromagnetic 3D system. But I've termed the concept of what I call functional accuracy. Is it going to show me what I need to know as an instructor in golf to know how far are you turning your shoulders? Okay, I could be off 3 or 4 degrees, and that's kind of typically what we've been seeing is 3, 4, 5 degrees here and there. But it still shows us the shape of the curve. It still shows us the timing of the curve. And obviously, because we're a front view, getting things that are depth are going to be much more difficult. So we're also working on a down the line so that you can, the model can be trained a little bit more. And the beauty of AI, as you probably know, is the more you train it, the better it gets. And so we're continually adding extreme swings. Does it know about somebody who doesn't do the normal things in a golf swing? I don't know if that answers your question.
Are there any other sports, or maybe even something, a field beyond sports, that you could see this technology really, yeah, I see you already get my question.
Anything that moves. I mean, it could be clinical analysis, could be gait analysis, could be reaching and grasping, slip and fall. It's got a wonderful range in the rehab market as well. But I'm an athlete, I'm a sports guy, and so we focus mostly on sports. And it seems like golf is always the first one that everybody thinks of. But of course, baseball, of course, tennis, and then all the team sports. You could even use this for, volleyball or soccer. And it already is being used in those areas, but not through SPORTSBOX. So fitness, I mean, you think about Tonal and you think about the Mirror and those new apps that are coming out to train you at home. Well, now we could say, well, did you touch your toes? How well did you touch your toes? Did you do that exercise the way you were supposed to do it? So yeah, golf is just the beginning.
Hi, Phil. Thanks for coming out. Great presentation. I really appreciate the old photos of you and the technology. My question relates to the technology. I see it works great for like an individual golf swing, but can you speak a little bit about the possibilities of capturing, let's say, you just mentioned like a volleyball game or a soccer game or a hockey game, more than one athlete at a time, maybe on a larger scale?
Well, yeah, we have actually been approached by USA Volleyball because they typically can have a camera right at the end of the volleyball court and you can see all the players on the volleyball court. And so we've been asked, can we treat the volleyball player as just an XYZ coordinate, basically center of gravity? You could think about that and track them around the court and look at the different strategies, but not just on an XY in a 2D. Let's look at how high they go too, if they're spiking the ball or if they're blocking and that sort of thing. So yeah, what the technology there was, you have to find each athlete, so you come up with a bounding box and you put a bounding box around the athlete. So there's multiple different types of AI technology being used along the way. So once we've got a bounding box and we've decided, oh yeah, that's a person, that's a person, that's another person, then we put our stick figure on top of it using pose estimation. From that, we calculate the center of gravity. And the cool thing about like volleyball or any of the field sports is they have markings on the floor. So we can use those markings as calibration and get decent analytics from it.
We'll do one last question.
Hi, Phil. Thanks for your talk. You spoke earlier about the accuracy of the data. I was wondering if you could touch on the within-subject reliability for that type of actionable data that you were talking about.
Yeah, we're undergoing all of those tests at the moment, and I agree. The reliability of what we get from one swing to the next is important. But we have seen that we're within a few degrees. And the cool thing about the AI technology compared to the marker-based technology is the marker-based technology has to be applied by somebody. And so they've got to put the markers in the right places. And they've also got to worry about all the skin motion. So functionally, from a functional point of view, we don't have to worry about that sort of stuff, especially if we're capturing that person over that particular series of trials. They may be having 20 swings. So our functional accuracy and the repeatability is pretty good. I won't give you any numbers at the moment, but you can talk later if you want.
Great, thank you
It's
so much.
without user intervention, so that's kind of one of its benefits.
Great, thank you so much.
Thank you.